Good morning, sir. I am Kunal Mukherjee and I am a student from A2 slot. And today we are going to perform fabric defect classification. So, for fabric defect classification, the main aim of today's experiment is to use GLCM, that is, using the GLCM and LBP features for the class feature extraction, and after that on combined features, by scaling them, by reducing them, we are going to apply machine learning model on that for creating an automated fabric defect classification system. So that is the aim of today's experiment, and the data set was taken from Kaggle. It was the grayscale resized to 64 pixel data set. It was imbalanced, so the results are not in much favor of the actual accuracy. So, as moving further, so now what is the problem? The main problem is manual inspection of any fabric is quite time consuming. So what we are going to do, we are going to develop a machine learning model which is going to use GLCM and LBP for feature extraction. Using these feature extraction, we train the model, and when we train the model, what happens? It extract the features, it gets trained, and then it uh, takes the image of any input image, and it can classify that it is a defective fabric or good fabric. Basically, it can't classify much, but it can classify at least it is defective or it is good. Now, dataset we have taken from Kaggle. So from Kaggle we have taken EILDA dataset, which is basically a dataset for fabric defect, a wide dataset with good images, but there are very much less images with the defects, that is object, hole, oil spot, or thread errors. But for good, it is much more. So the dataset has one challenge to deal with, that is, it is imbalanced. So if our objective is not to detect them in the classes of each individual defects, that is object, hole, oil spot, thread error, we can directly uh, keep good as one class and defects as one class. Then also there will be a high imbalance, because for good there will be 23,000, and since it is around 500 for each, so it will become 2,000. So then also there is a 10x of imbalancement still persist. So this is not a good data set, but this is the most viable and wide data set in terms of fabric classification which I have got. Pre-processing steps, pre-processing grayscale. So grayscaling the image, but the thing is, for this data set, the image was already converted into grayscale. Resizing the image, so it was already resized, but still was resized and converted to grayscale in the pre-processing method for better results that we can get. If there is some defected image, so it will not create, it will not turn into error. So it was already converted. And feature extraction, for feature extraction we have GLCM model, and for feature extraction we have also used LBP here. So GLCM, that is gray level co-occurrence matrix, it helps for capturing the texture based features, and for LBP local binary pattern, it detects finer texture variations. And then we have normalized, that is we have scaled up into normal values after combining the features for training on the combined results. Now, what is GLCM? Gray level co-occurrence matrix features. So it is a statistical method that captures the texture patterns in an image by analyzing the special relationship of pixel intensities. It extracts four important features: contrast, correlation, energy, homogeneity, and the range is as given in the example. And then we have LBP, that is the local binary pattern. So local binary pattern is focusing on fine-grained texture patterns, works by comparing each pixel with its surrounding pixel based on intensity, then converting these comparison into binary values. So binary value, so what happens? It captures the structural pattern in the fabric and particularly the useful patterns for detecting the defects in the um, defects in the fabric, and then converting comparing with the neighboring values, and then converting it into binary values, which normalize the values and then detects the minute texture variations which are there. Then model selection. So now comes the main part, that is model selection. Model selection, as we don't know which model would give better results, so we have tested on four models: logistic regression, random forest, gradient boosting, SVM, using bagging technique. Then after training, using the combined results of GLCM features and LBP features. First, we have extracted the GLCM features, then we have extracted the LBP features, we have combined them, we have scaled them into the normal values, and then we have used the models. So for training, we have used logistic regression, random forest, gradient boosting, SVM. We have used SVC with particular hyperparameters for each. For logistic regression, it ranged from 92 to 93, for random forest 91 to 92, gradient boosting 92 to 93, SVC again 92 to 93. But at minute level, the best result was with SVM. It gives around 92.6, that is approximately 93% of result what we got using SVC technique. And that's why the final model and the final accuracy matrix, precision, sorry, confusion matrix, and the results were given based on the SVC technique that we have used. Now the result what we have got is, so that when we go we have trained the model with augmentation also and without augmentation. So when we train without augmentation, so we have seen that when we go with augmentation, we have performed some rotation, translation, all those things. After that, it loses much the contrast of image and it generalizes the image since it is the fabric image data set. So the defects were highly impossible, becoming impossible to classify. So good images were still classified since accuracy is a bit reduced 91%, but without augmentation, the precision was very high. Recall for a good fabric was good at higher level, and accuracy was also bit increased because it does not lose much into its contrast. And so in this particular case, without augmentation was a helpful case rather than with augmentation. Now, what were the observational limitations? So, observations made is that texture-based features are effective, feature extraction methods are effective, but this is a very imbalanced data. Like we can imagine that 23,000 for good and around 2,000 combined for defect. So there is a 10x of difference. So these differences kind of difference between a train test split. So it is a very wide difference which causes into bad results at the end, like for the defects. Uh, since any dataset publicly available for this is at with very low images, either imbalanced or with low images, so the accuracy somewhere is going wrong. And similar textures, like if there is a oil spot and there is a hole, so it may on the corner just classify into a same thing. So deep learning models, perceptron models could enhance this issue, could solve this issue. So conclusion, the best result we got was 93% using GLCM and LBP features which were effective. But we can do much more handling by this imbalanced data set using SMORE. and we can use some deep learning models which can increase the results, optimize the feature selection techniques, and basically these method can solve the issue that we were facing currently. So thanks a lot, sir. This was my presentation for experiment 9, dated 8 March 2025. Thank you.